So today, what I want to look at is how we can pull out some critical information about polynomial functions without doing much work, but just at looking at the algebraic representation. So what I want to be able to do is look at the algebra and get some information about the graph. So why don't you follow along by taking some notes for yourself. Pause the video as much as you need to, and let's see how we do. So here's a function, and you'll notice it's what we call a quintic. It's a fifth power function, and it's got all these terms going on, and this is what I'd like to be able to do. First of all, I'd like to be able to describe the end behavior, and now I want to look at this down here. So we just had a lesson on end behavior, and if you need to go back and rewatch that video, it would be a good idea to rewatch the video. But let me remind you that end behavior is really determined by this number right here. So looking at that, what I'm going to do is I'm going to imagine that my x value is a really big X. So let's see. Let's just look at what happens when I take y equals 3 to a big negative x to the fifth. Well, a negative to an odd power is negative. A negative times 3 is going to stay negative, so my argument is this is going to be a negative number. So in terms of end behavior, as x goes to negative infinity, y is going to be going down. So y is going to go down. And then to see what's happening to the right of the graph, as x goes to the right, as x goes to positive infinity, I'm going to let my x in my leading term, just this term, the rest of the stuff doesn't really affect end behavior, I'm going to let x be a big positive number to the fifth power. Now we know that any positive number to the fifth power is going to stay positive. And a positive times 3, well, that's just positive. And that tells me that this graph ends up. So it starts down, it's going to wobble around a little bit because of this stuff, and it's going to end up. So I have that idea of my graph. But then I ask, what happens when x is 0? When x is 0, what's the y value? Well, when x is 0, I guess this whole term becomes a 0. When x is 0, this becomes a 0, this becomes a 0, and this becomes a 0. So when x is 0, what's the y value? Well, this is my y. Y equals 8. So that gives me 0. That gives me the point 0, 8. And what is this special point 0, 8? Well, 0, 8 is the Y-intercept. And that is a very special point to us. So what are we going to do with that? Well, why don't you see if you can fill in the blanks for these functions. I would like the end behavior, and I would like the Y-intercept. So now is a great time to pause the video, see what you can figure out on your own. So this is a problem where we need to find two things now. Now we're looking for end behavior and we're looking for the Y-intercept. So if we think about end behavior, again, end behavior is all determined by this leading term, this term out in front. And if we imagine, I guess I need to grab a pen here, if we imagine that x is a negative number, so what does y become when x is a negative number? So I'm going to put negative 7 times a negative number to the fourth power. Well, anytime you take a negative to an even power, it just becomes a positive. And when I take negative 7 times a positive number, it becomes a negative number. So as x approaches negative infinity, it looks like y is going to be going down towards the negatives. And then I could do the same thing for when x approaches positive infinity. As x moves to the right, as x is going to become a bigger and bigger positive number, we have negative 7 times a positive number to the fourth power. And again, anytime you take a positive to an even power, it stays positive. Negative 7 times a positive is a big negative number, so this y value is going down towards the negatives. And if I'm looking for my y-intercept, I let all these x values, all of them become 0, and I'm left with y equals 1. So the y-intercept, when x is 0, y is 1. Why don't you go ahead and take a look at this next one and see if you can do this. So pause the video and then come on back. Hey, welcome back. Hopefully you checked the in behavior, and here you got that y is going up as x goes to the left. So as we move along our graph, we're expecting the y value to end going up. And we've got some wobbling going on here. And as we move to the right, we have y value going down. They're going starting high and ending low. So this thing will end up going down. And this time, when we let x become 0, you'll notice that everything is 0. As a matter of fact, if you really think about it, the y-intercept is always determined by the constant, the number that's by itself. And here, the number that's by itself at the very end is a 0. So the y-intercept in this case turns out to be, the origin. Boy, I'm not very good writing with this mouse. Okay, so let's move on. This time, notice don't worry about graphing this in Desmos. We don't have to do that. But this time, notice I gave you the polynomial in factored form. So let's think about what's going on here. I need to find three things now: the in behavior, the y-intercept, and the roots. And so when I think about this problem, what I'm kind of thinking is, well, if I want to determine, say, the in behavior, I want to know what that leading term is. And when I start multiplying all these things together, it becomes a really big polynomial, but all I care about for in behavior is the first term. And you see that we will eventually get, what is this? X times x, which is x squared, times another x, which is x cubed. So we eventually get y equals x cubed plus, well, some stuff. And again, that stuff is responsible for what's wobbling around between my in behavior. And then the only other thing I really care about is finding the y-intercept, those constants. What's the constant going to be? Well, if I take negative 2 times 3, that's negative 6. Negative 6 times 1 is still negative 6. So this part right here is going to help determine the in behavior. Think about a nice big negative number here for x. And when you have a negative to the third power, it stays negative, which means my y is going down to the negative numbers. And as x becomes positive, put in a really big positive number. When you have a positive number cubed, it stays positive, which means y is going up to the positive values. So I know this graph is going to start low, it's going to wobble around, and it's going to end high. Now, what about the y-intercept? Well, the y-intercept happens when x is 0. And when x is 0, all this stuff here zeroes out, and we're left with negative 6. And finally, we have the roots. Now remember, roots are what you get when the graph crosses the x-axis. And when the graph crosses the x-axis, notice that we get roots whenever the y is 0. So if I let y become 0, I can use this factored form to say x is, what is x? X is 2. X is negative 3. And x is negative 1. So my root, this parenthesis doesn't belong here. My roots are 2, 0, negative 3, 0, and negative 1, 0. So maybe you can take a look. This is what we'd get if we graphed this thing. If we actually graphed this in Desmos, notice that the graph, as we move to the left, as we move along this graph to the left, that the y value is heading down. And the in behavior as we move to the right is up. So this graph starts way down here and it ends way up here. Notice the y-intercept right there, let me just put a green mark right there, is negative 6. And notice that we have roots when x is 2, that's this point, when x is negative 3, that's that point, and when x is negative 1. So we were able to pull out some pretty interesting parts of this graph. 4 specific points, the roots and the y-intercept, and the end behavior just by looking at the graph. Well, why don't you try this problem here all by yourself, and then we'll come back and check and see how you did. All right, so welcome back. So the first thing I'm going to do is I'm going to look at end behavior. And so I'm going to multiply, x times x, which is x squared, times another x, which is x cubed, times another x, which is x to the 4th. Don't forget about this negative out in front. And I get that this equals negative x to the 4th plus some stuff. And just knowing this leading term right here, I can put a negative value in for x. A negative to the 4th power is positive, but this negative right here turns it around and makes it negative, so y is actually headed down to the negatives. And when I put a positive in for x, a positive to the 4th power is positive, but this negative out in front is going to turn the positive into a negative, making it head down. By the way, let's not forget the order of operations. Notice that exponents take precedence over this negative, so the negative is not being affected by the 4. It's an afterthought. Now, the y-intercept. Well, I'm going to get the y-intercept by looking at, let's see, negative 1 times 1 is negative 1. Negative 1 times negative 2 is positive 2. Positive 2 times 3 is 6. But let's not forget there's a negative in front. So at the very end of this, I have a minus 6, which means that my y-intercept is at the point 0, negative 6. And finally, the roots. Well, we have a root at 1. We have a root at negative 1. Remember, the roots occur when y is 0. And when y is 0, we use the zero product property. We have a root at 2. And finally, we have a root at negative 3. So we have 4 roots. And sure enough, if I show you what this looks like, you can see the graph starts down and it ends down. We have a y-intercept at negative 2, 4, 6. And we have roots at 1, at negative 1, at 2, and at negative 3. Real quick, if you look, here is an algebraic representation of this graph right here. And you'll notice at negative 2, 0, we get what's known as a bounce. The graph bounces there. It doesn't cross, it bounces. And that's a root, but we call that a double root. And when you're looking at the algebraic representation of a graph and you see, boy, I don't really write well with the mouse. When you see a root like negative 2 that's being squared, it tells you it's going to bounce. And then if you see a root to an odd power, what happens is it does cross through. So we do cross here at 1, but it gives a little wiggle. And we'll talk about what that wiggle is later on. It has a name, and we'll define it. It's an inflection point. But we'll define what it does later. But just something to keep in mind. So one more problem here to take a look at. Pause the video and try it. And let's see what we get. Okay, welcome back. Hopefully, to find the end behavior, you took a look at x times x squared, x cubed, x to the 4th, x to the 5th. So this is x to the 5th, and hopefully you did the math and you realize that this is down and this is up. And then when you went to expand it out for the y, you saw that 2 times negative 2, positive 6 times positive 6. Ooh. Do you notice that there's no constant at the end? So the y-intercept here is 0. And then I'll let you find all 5 roots.